the recording. I don't want this card again. Yeah, so I wrote up a few things that I wanted specifically to go over, but instructor wanted you guys to basically learn Chapter 6 on your own, right?
Yeah.
Is that my understanding?
Yeah, can we do that?
Yeah, because Chapter 6 is like really freaking important stuff, and...
And that's what they will skip?
Huh?
That's the chapter they will skip?
Yeah, dude, that's just the chapter to skip. You know, some of the most complicated concepts. Oh, let's plug in my computer real quick so it doesn't die during the recording. Computer, get some powers. There you go. Nom nom nom. Eat that power. Okay. Yeah. So I want to talk about that. Yeah. Let's just talk about. Let's just do a real quick run through of Chapter 6. Some of this has already been discussed in lecture. Oh, sweet, different colored chalk. That will be really useful. But all right, I want to burn through the first few sections of it real quick. Let me just flip to those pages just to make sure I don't leave out anything real good. So chapter starts off and they're like, hey, there's this stuff, there's this concept, it's called enthalpy. Start off with a discussion of enthalpy, which for our purposes, oh, we already discussed that in chapter 1. That's fine. We can really just talk about this as heat exchange. Like H, we more or less consider this to be heat exchange, or really energy. Let's not use heat. Your energy exchange for a reaction, or delta H. Yes, and at a constant pressure, it's the exchange of heat. Right. Let's stick with heat, actually. Delta H equals Q, or heat, at a set fixed pressure. That's fun. Are we going to use that very much in class? No. What is most important that they really touch on in this first section where they discuss enthalpy there are two very important things. They briefly touch on homolytic cleavage and heterolytic cleavage, which Dr. Hill has already mentioned, also briefly mentioned in lecture. But homolytic cleavage, homo, same, is we have a bond, say hydrogen-hydrogen bond. When this bond breaks, each side gets the same amount. So our bond, which is made up of 2 electrons, each one of those electrons will go to one of these hydrogens. And to show that, we use 2 different arrows. Each one of them only has half of its head. So a normal arrow has this full head. That's a terrible looking arrow. A normal arrow has this nice full head, while in this case we have half arrows. And so those show a single electron moving. This is homolytic cleavage. We're going to not see a lot of homolytic cleavage for the most part. It's not super common in the chemistry we'll use. And so this will give us 2 hydrogen atoms, which each have a single electron. On the other hand, we have heterolytic cleavage of hydrogen, dihydrogen. We're going to use a whole-headed arrow, normal arrow. And I'm just going to arbitrarily show this going to one of the hydrogens because they're both equivalent. So this now represents 2 electrons moving. An arrow with 2 ticks at its head represents 2 electrons moving. 1 tick at its head is 1 electron. Pretty good system. And, you know, they weren't goofing around too much, whoever came up with this. And so the result of this is these 2 electrons are going to go to 1 hydrogen, and the other hydrogen will have no electrons. So this will give us H plus with no electrons, and a hydrogen with 2 electrons, each minus a hydride. Heterolytic cleavage versus homolytic cleavage. Heterolytic cleavage is, I'm not going to say exclusively, but will generally give us a charged species and results in formation of charged species. What else did they go over that's really fun in this chapter? They really quickly discuss how enthalpy relates to reaction energy diagrams. So reaction energy diagrams, we've seen these just a tiny bit in class thus far, but they come up quite a bit, and they're pretty important to us in organic chemistry. We use them to help us understand reactions and simplify many aspects of them. But your standard reaction energy diagram has on the bottom axis the reaction coordinate, and that basically just tells you where in the process of a reaction you are. So let's say we're studying the reaction of A going to B. So for your standard reaction, our y-axis, is energy. So this shows us the relative energy of different species that will be present during a reaction. So a simple reaction, A goes to B. Let's say this is an exothermic reaction. So we have 2 different types of reactions. We have exothermic reactions, which have a delta H that is negative. They release energy. In this case, A starts off at a relatively high energy. And so for most reactions, we have this initial barrier in energy that we have to pass, which we'll talk about a little bit more. Actually, let's just talk about it. We'll talk about it in a second. So in this case, A goes to B. This is a standard or general-looking reaction energy diagram. And so in this case, if we wanted to talk about delta H, we would look at the difference between these two the energy difference between our 2 species. Right. And so in this case, this is an exothermic reaction. B is less than A. We have a negative shift in energy, negative change. So this is an exothermic reaction. Let's talk about this hump really quickly that we have. We're pretty much always going to see these in reaction energy diagrams. What is this? What's going on here?
It's the energy barrier needed to form from reactants to form products.
Correct. This is our energy barrier. This is the energy barrier between our reactants and products. So for almost every reaction, we have to reach some unstable state that is in between our reactants and products. And we kick our energy up to this unstable state, and we drop into either reactants or products. And so this is referred to as our activation energy. Activation energy. This difference in energy here. Just to show the opposite of the exothermic, I can write this down, but we also have endothermic reactions. Those that take in heat. Hey. Endothermic reaction, you can probably guess, our product is going to be at a higher relative energy, higher in energy relative to our starting material. So we might have a reaction coordinate of A going to B here. Ta-da! We can see, based on looking at this, that in general, endothermic reactions are going to be harder to get going because we're going to have a very frequently larger activation energy barrier. We have to hurdle over it. That's not always the case.
So if you have an endothermic reaction, what if you put a catalyst in it? Won't it drop a little bit?
Good question. If we have an a catalyst in here, we may not need as much energy to get this reaction going. So this might be the case with a catalyst. Yeah, catalyst can lower our activation energy. We might see, for this case, if we were to throw a catalyst in here, it might look something like that. So they lower the activation energy, but they don't change the overall fundamentals of the reaction with delta H. That's an important thing that sometimes people get confused about. They think that a catalyst will change the enthalpy, or the change in enthalpy in a reaction, and that's not the case. They don't, yeah. That is not what we are looking at. Okay, so we really want to talk about entropy, but let's just really quickly, last thing about enthalpy I want to say for now is just how we can calculate enthalpy using tables. So they're really fun tables, and they tell us bond dissociation energies. Are they bond dissociation energies in this table? They are bond dissociation energies. So that tells us how much energy is released when we break a bond. So, and that they have all sorts of bonds in them. You can apply them to all sorts of groups. So let's just say we have okay. Let's just say we have some fun molecule like let's just put a bromine on you, and we're gonna react you with some OH minus to produce some OH. Let's put a P minus also. Balance our reaction. Cool. So we do this reaction. If we want to figure out the delta H for this reaction, how can we do that? Well, we can calculate this. We can use tables inside your book. There is a wonderful table on page 238, table 6.1, and it shows values such as the bond dissociation energy for a hydrogen-hydrogen bond, which we're not super interested for our molecules, but we would be interested in the bond dissociation energy for a carbon-bromine bond, since we're clearly breaking one of these. And we'd also be interested in the bond dissociation energy for a carbon oxygen bond, and also for a oxygen-hydrogen bond. So when we want to calculate delta H, we can use a table, and we can do a fun summation. We can take the sum of all of the bond dissociation energies for our reactants. Okay, am I doing this right? Yeah, this is our dissociation energies. So our reactants are all dissociating. And we can subtract from this the bond dissociation energies for our products. So all of our reactants are dissociating. We're forming all of our products and subtracting out dissociation. Negative of dissociation is association or formation. So for this reaction, we would want to look at, and do this really annoyingly and painstakingly, we would calculate the energy for each one of these bonds. So for this example, let's get rid of this Magoo face over here. Yeah, setting this up right.
Is there no carbon attached to the bromine at the top?
This one, we've got this carbon bromine bond.
Oh, but there isn't one at the,
On the other side,
on the, like, at the really top.
like,
I mean,
do you want to come up and show me?
She's saying if there's a hydrogen bond with the bromine.
3 carbons on
I am confused. Oh,
it.
come show me, please. I'm a little confused.
Like no carbon over here connected to the bromine?
No, we just have this carbon and then just this. Bromine with lone pairs. Bromine only wants to form one bond. This is an ideal bromine situation. Cool? Okay. So, lost my train of thought. Right, so we would look up the bond dissociation energy. Sorry, yeah. We would look at all the bonds in there, and we can say, okay, we have 1, 2, 3, 4, 5 carbon-hydrogen bonds. 5 carbon-hydrogen bonds. We have 1 carbon-carbon bond plus carbon bound to carbon. And we have 1 carbon bound to bromine. So this would be, if I put in the values from the table here, which let's just write some of those in. Oh my gosh, I guess this table doesn't have everything I want. Can I use some values that are approximately close? All right, so maybe this table isn't that rad. I didn't look it over that thoroughly. My mistake. But we can extrapolate some values from it. You could say that this is approximately 435 kilojoules per mole. And this carbon-carbon bond is approximately 368 kilojoules per mole. And the carbon-bromine bond is approximately 285 kilojoules per mole. So we would multiply this first value by 5 and add the rest of these values together, and that would give us the total summed value of all the bond dissociation energies for our reactants in this case. Oh, you know what? I totally left out the OH. The OH is important. So we would also have to add into that our OH bond. My mistake. Which doesn't seem to be on this table. I completely retract what I said. Oh, no, there it is. Okay. Table, you're not that bad. So there should also be our OH bond in here, which is another 498 kilojoules per mole. I don't feel like adding this up because these problems aren't super fun. Should I add them up? These problems aren't super fun and not really the core of what we're doing here. So I feel like we should just blow by them.
Wait, was it 98?
Yeah, 498.
Oh, 498.
3,326?
Yeah.
Okay. Cool. So this was actually kind of a giant waste of time, though. Because if we wanted to do this more efficiently, we could say, oh, well, we still have these 5.
Subtract it?
Yeah, we could just cancel out all of the bonds that stay the same. So we could say, oh, you know what? We don't even need to consider these 5 CH bonds. Those are in both the starting material and the product. Oh, this carbon-carbon bond is in both the starting material and the product. The OH bond is in both the starting materials and the product. So really, to do this problem super quick and dirty, all we would need to focus on is the difference in bond dissociation energies between the carbon-bromine bond and the carbon-oxygen bond. If we were doing this really nice, though, we would, yeah, the tables, the values vary quite a bit. You know what? Yeah, these tables aren't super great. There is quite a bit of variation between a H2O bond and an OH bond. The oxygen is not on a carbon, and when it is, it's an alcohol versus just water. Whatever. Just wanted to demonstrate how we do these. They're not super great. Let's move on to something way more fun. Enthalpy's cousin, or maybe its sibling, entropy, which, yeah, is not really emphasized super hard, but I think entropy is super rad. Drives the universe. So entropy is, to sum it up very simply, is a change in order. Systems like to go from an ordered state. The typical example is, they have a few nice examples, but they like to go from an ordered state to a disordered state. I like the example the book shows us where we have two vessels. We have a little stopper between them that we can open and close. Let's say we have a ton of particles, a lot of gas in one vessel and no gas in the other. Well, the second we open this valve, we're going to see the gas distribute itself between the two vessels. It moves from an ordered state, where we only have gas in one place, to a disordered state, where we have gas in multiple places. The other way I like to think about entropy is, entropy is just rad. It's just moving things, it's a change in order. So when we have a positive entropy value, we have an increase in entropy, we have an increase in disorder. So nature generally wants us to have, shut up cell phone. Nature generally wants us to have positive entropy values, and overall entropy values for every reaction is positive if we consider the system and our surroundings, but don't worry about that. What?
Which a positive means that,
We've increased our disorder.
like, the reaction goes forward, or is that something else?
So let's talk about that. What does that mean in terms of reaction? So increase in disorder might be a particle breaking down. So if we have A dissociating, or let's say we have just this molecule that's A bound to B. This dissociates to give us A, let's say you're A plus and B minus. I said those wrong. A minus and B plus. This reaction would, it's not going to be charged. If this just goes to A and B, this would most likely have a positive delta S value. Because we've increased the disorder. We used to have one thing, now we have two. Two things, more chaos. More stuff is going on. Conversely, a reaction where we take a bunch of things and we mash them together into one. Let's say we have like 3A plus 2B gives us C. This reaction is most definitely going to have a negative entropy value. We have decreased disorder. We have created order by taking all of these molecules and putting them together as one thing. So negative entropy is generally not favorable for reactions. Generally, a reaction is going to generally be more favorable if we have a positive entropy. And that sort of brings us to the next topic that these two guys funnel into really nicely, which is Gibbs free energy, relates entropy, enthalpy, and temperature to tell us about a reaction. So enthalpy is our delta H, you are our delta S, and we have Gibbs free energy just with an E. And this value we use for lots of thermodynamic calculations, lots of calculations regarding our species, also kinetic. But for our purposes, we're going to keep it pretty simple, and we're going to say that the Gibbs free energy tells us about let's see how the book phrases it. I'm a little curious how they want to handle that. But I would say it tells us how a reaction is going to perform, whether or not it will perform spontaneously or non-spontaneously. You know, that's the word I needed. Tackles us about a reaction's spontaneity. Can I spell that? Nay. I don't know if I spelled that right. You guys just need to know the word. Spontaneity. So Gibbs free energy is determined by the delta H for reaction minus the temperature times the change in entropy. And so for a reaction where this is negative, that's going to give us a spontaneous reaction. So a negative value corresponds to a spontaneous reaction. That means the reaction is just going to, if we put our reactants together, they will simply proceed to react. A positive Gibbs free energy value is opposite, a non-spontaneous reaction. This is a reaction that we just throw our reagents together at a given temperature, they will not react. And if we have a value of 0, this means we're in equilibrium. The reaction is proceeding forward at the same rate that it is proceeding backwards. We're making products at the same rate that products are making reactants. Let's break that down a little bit, because I think it's very interesting and informative. So if we want a reaction that is spontaneous, we would like to have negative values throughout here. So a negative delta H means is favorable for a spontaneous reaction. A exothermic process is favorable for a spontaneous reaction. And I kind of rationalize that in my head. Whenever I think about exothermic processes, I think about combustion. And combustion, once you get it started, it just goes. It's a very spontaneous process. That's how I always just rationalize that. And I say, okay, that makes sense, right?
Spontaneous is always exothermic?
Not always.
Okay.
Not always. So maybe we have an exothermic processes generally are more likely to be spontaneous because we would be putting a negative value in for delta H. And to have a spontaneous process, we should also ideally have a positive value for delta S. So a reaction that increases disorder. So if we have something that releases heat and increases in disorder, that's going to be a favorable reaction no matter what. Now, if we have an exothermic process, but it's also going to decrease our disorder or increase order in our substrate, now we have a little balancing act. Delta H is negative, but we're subtracting a negative term here. So in this case, we're going to want to run our reaction if we want it to go forward. Our temperature becomes very important. If we have a very high temperature, that's going to amplify the impact of our negative delta S. So if we have a high temperature, at high T, this is going to be non-spontaneous. This is going to not work because this term will become real big and it'll outweigh our delta H being negative. So at a high T, non-spontaneous. At a low temperature, though, the negative delta H is going to outweigh this negative delta S. So this term will be larger if we have a low temperature. Low T, spontaneous. And so we can have the reverse of this. If we were to have a positive delta H and a, what am I doing here? Positive delta H and a positive delta S. Well, for this reaction to work, we would want to run it at a high temperature. Blurp, 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 blurp. Lost my train of thought. Run at a high temperature, right. And if we have a positive delta H and a negative delta S, if we have an endothermic process that decreases entropy, that increases order, well then this reaction is just not really going to work very well. There's no way to get this to become spontaneous. This is just going to be non-spontaneous. This reaction won't be very favorable at all because, yeah, we'll have a negative term here, or I'm sorry, a negative, yeah. This will be positive, and subtracting a negative term gives us more positive. Positive delta H means our reaction is non-spontaneous or just simply won't go. The reverse of that process would be very favorable at that point. So, Gibbs energy. This also is not going to come up a ton in our studies. but it does get splashed in here and there for flavor. It's good to know about. Let's really quickly talk about equilibrium a little bit more. Because equilibriums will come up a lot. Maybe not in the depth discussed in this text, but that's actually a fun table. Table 6.2 is pretty fun, just at a quick glance. Although I've been known to be completely incorrect about whether or not tables are cool. So equilibrium. Flashing through. If we're just going to quickly sum up equilibrium, how do they want us to do it in this text? Okay. Yeah, I like your example. Cool. Let's say we have the reaction AB goes CD, and we'll put in a fun reaction energy diagram for this. Energy, this will make this free energy, G, and this is our reaction coordinate on the x-axis. We've got A plus B and C plus D. And yes, we have an equilibrium. So these arrows, instead of just representing this as A plus B goes to C plus D, for a non-reversible reaction, I'm just going to use an arrow like this. I frequently use arrows like this. I might do that because I'm lazy. But if we want to show a reaction that is in equilibrium, we want the reader to know that it's in equilibrium. We're going to use these arrows, these double half arrows that point in either direction. That says, hey, this is going back and forth. A and B are combining to make C and C and D are combining to make A and B. So if we wanted to know a little bit more and we wanted to do some fun calculations and figure out, all right, well, if we have a mixture of A and B / C and D, what is the composition of either? We can use our equilibrium.
Ice table.
Oh, yeah, ice tables.
I never want to see them again.
Yeah, well, we won't really do them. I just really want to talk about this for a hot second. Right, KEQ is equal to the concentration of our product divided by the concentration of reactants. That doesn't really say it nicely though. So for this experiment, for this particular one, we're going to multiply together the concentration of each reactant. So this one would be the concentration of C times the concentration of D divided by the concentration of A times the concentration of B. If we had a reaction that was like 2A plus B goes to C plus D, well, we would just multiply in A twice. So we would say, all right, concentration of C times the concentration of D, this divided by concentration of A, there's two of them, times the concentration of A times the concentration of B. And we would just simplify this to be A squared. Other important equation involving KEQ, so we can relate and learn the equilibrium constant, G natural log delta, yeah. We learn the equilibrium constant if we know the delta G for a reaction. And we can figure out the delta G for a reaction from tables and stuff, so there's all sorts of fun math that we can do if we were Gen Chem students. But we're not. But it is important to see here that temperature can influence our equilibrium constant. What other things can influence our equilibrium constant other than temperature? Are you guys not talking about that? No, we're going to talk about that later. All right. Right, equilibrium constants, yeah, really only going to be affected by temperature. And I think that's all I want to say about equilibrium. Is that all the book really wants to say? Yeah, we're good. Equilibrium constants, hooray! Book quickly hits on kinetics next. golly, I really don't want to get into kinetics, but what do you guys kind of have a lot to say about kinetics? Okay. Yeah, we should talk about kinetics. Yeah, all right. So kinetics, when we talk about the kinetics, we're exploring through rates of reactions. We're mostly going to be concerned with rate equations, which K times the concentration of reactants. So the rate of reaction, yeah, is going to be equal to K, who is a constant. Yeah, it's constant. The reaction constant, rate constant, rate constant. And yes, then we have the concentration of our reactants. And each reactant is going to have an order. So we can have 0th order, where the concentration of a reactant, let's say we have, well, I'll just write these for A's, is A to the 0. So in this case, this concentration, the concentration of this reactant doesn't influence the rate of the reaction at all. Or we can have a first order, where we'll raise this to the first, so it has some impact on the rate. Or we could have a second order rate constant on this guy. Ta-da. So this is the order with respect to a specific reactant. So let's say we have a reaction. Should have left that out, sorry. It's super complicated.
I got it.
Let's say we have a reaction where A plus B goes to C. And we learned that this reaction is, let's say, first order with regards to A, and first order with regards to B. This overall reaction is going to be, overall this is going to be a second order going to be a second order reaction, where it is first order with respect to A and first order with respect to B. So that's a little confusing, but again, the overall order for a reaction is going to be the sum of the order for each individual reactant who participates. Just a little confusing with order this, order that, order your mama. So to get into the factors affecting rate constant, okay, yeah, great. Or factors affecting rate, yeah. So the rate constant can be influenced by a few things. So activation energy can influence our rate constant. Say we have reaction with a big activation energy in a reactant with a very small, by comparison, at least in the scale of these drawings, activation energy. So at the same temperature and all the otherwise same conditions, our lower reaction should proceed much faster. Well, why is that? Other than it just has a lower activation energy. Why will it react faster? We can make a fun diagram that tells us at a given temperature, the number of molecules with a specific amount of, this is kinetic energy, but no, it's probably, yeah, distribution of kinetic energy. This guy kind of looks like this. Down here we have energy. So the energy, this activation energy comes from molecules colliding together. It's not like they get together and shake hands and say, hey, would you like to do a reaction? They smash together in equilibrium, or not in equilibrium, in solution generally, sometimes in the gas phase, rarely in the solid state, but it comes from them colliding. So it makes sense that the faster they are, the more kinetic energy they have, the more likely they're going to get into one of these collisions that leads to the reaction. So if we have a high activation energy, that means we need a lot of kinetic energy. And maybe only this much, if this is our required energy, only a small amount of the total number of molecules can do this reaction. If we need way less energy, then we can see, lower activation energy means more molecules at a given temperature will be able to do the reaction. More molecules will have the energy needed to get it done. So low activation energy is going to correlate to an increased rate. At the same time, or on the same note, if we increase temperature, things get hotter, things start vibrating and moving around faster. We increase the overall kinetic energy of our medium, be it a solution or gas phase, whatever. So this diagram, if we have a high temperature, it's going to get spread out more and shorter. So at a higher temperature, let's get rid of this initial shading. Our activation energies are not going to change. And we can see at a higher temperature we have an increased distribution of molecules that have the requisite energy to do this reaction. There are more molecules that are beyond our activation energy level, so they can just do this reaction. Go ahead. So cool, temperature influences that, and the book also talks about steric conditions, which they just don't get into. We'll talk about this more later in chapter 7, apparently. But steric factors, we'll save that for later because I want to move on to reading energy diagrams. Really, yeah, we should talk about that. I just want to talk about mechanisms, but does anybody have any questions? Actually, pause. No. Let's talk a little bit more about reading our.
The first half of the chapter, all conceptual stuff.
Yeah, it's largely conceptual. There's some maths in there.
Is he actually going to test us on this stuff?
I don't know. I would assume so.
It's like Gen Chem.
I would expect maybe. Yeah, it is pretty Gen Chem actually. It's a little maybe more in depth than Gen. No, this is all very Gen Chem.
Yeah.
All right. Well, let's just speed ahead just through reading transition states. I really like this point, actually. Yeah. Reading these energy diagrams, let's look at transition states in them and intermediates. Yeah. Okay. So a lot of reactions have intermediates. For example, in lab this week, if you haven't done it yet, maybe you already have, we did a reaction, the E1 elimination reaction. And let's just make a reaction energy diagram for that. Pretty sure our product's more stable. So we start with our methyl cyclohexanol. And this is converted to a carbocation, which is converted to our cycloalkene product. To make you nice. We'll just draw the primary product for now. So in this reaction, we have our reactant and our product. What do we call, does anybody know what we call this dude in the middle?
Intermediate?
Right, it is a intermediate. So intermediates are any stable species that are formed during a reaction and by stable species, I essentially mean in the center of one of these valleys. So when we form the, using my words, the carbocation, when we form this carbocation species, this isn't a very stable molecule, but it is at a stable point. It is certainly relatively stable to these peaks, which are called what? Anybody?
Phases?
Not that one. Any other ideas? Transition states. Call these transition states. So they're as we transition between stable species. You're going to go around that arrow. It'd be really confusing. That was terrible. That is confusing. Let's get you out of there. The tops of our peaks are our transition states. Gorgeous. Is there anything else real fun we should talk about? Yeah, the Hammond postulate's pretty fun. I guess it's not the most fun, but I don't think we'll actually be using it much. I kind of get a feeling Dr. Instructor will want to use it in a question. So the Hammond postulate, what the heck is that? It was invented by Dr. Hammond from Jurassic Park shortly before, I guess in the movie he gets away, but in the book he gets killed by a bunch of small dinosaurs after he falls down a hill, and he came up with it while he was dying on the hillside. It's a really intriguing story. Anyway, the Hammond postulate states that the intermediates in a reaction for a exothermic reaction they will resemble, in an exothermic reaction, resemble the starting material. And the opposite in a endothermic reaction. In an endothermic reaction, the intermediates resemble the products. So what the hey does that mean? Well, let's use it for this example I've drawn here. Get out of here, all you other words. So the first step of this reaction is a endothermic process, right? We are increasing our potential energy. Let me just draw in our product. And our second step is an exothermic process. We're releasing energy. We're going from a higher energy state to a lower energy state. Is that all you got? Really? All right, I guess we're not going to talk about that much in the text. But so for an intermediate species, for this species, what's happening here is our OH is leaving. In this step, our OH bond is breaking to give us these charged species. Well, since it's an endothermic process, our brain fart. Our intermediate is going to resemble, the product of that reaction more. Let's not get into this. It's really brushed over by the textbook, and not as important as nucleophiles and electrophiles, which is the next section, which we should definitely talk about because that's really crucial for drawing mechanisms. Any questions? I didn't go over that well.
How would we be asking questions about again?
That's the main thing that I'm like, I can't think of how this would be framed into like a test question, and I don't think it's really underemphasized in the text, and it's more useful for a physical organic chemist than what we're going to really be covering here. I don't know if Dr. Instructor is not going to really cover this, but I don't want to dwell on it too much. Let's not sweat it too hard. What we definitely need to sweat though is nucleophiles and electrophiles. At least some instructors think this, and I am one of them. Because if you can pick out nucleophiles and electrophiles and evaluate them, then you will be one step closer to totally kicking ass at drawing mechanisms, which are a big deal in organic chemistry. So if we can figure out and discern electrophiles versus nucleophiles when we approach a reaction, we can totally kick its ass. Wow! I'm not going to break this chair. I have a broken toe, so I don't want to mess with that. All right. I want to see what the text says right off the bat. I'm going to say what I want to say right off the bat. So, nucleophiles. What is a nucleophile? Anyone have a guess?
It's nucleus loving.
Nu-
Like,
Nucleus loving? Yeah.
so like anything that has like a lone pair or negative charge.
Exactly, yes. So I wouldn't say, well, nucleus works. Yeah, that is really how it breaks down, isn't it? Yeah, nucleus loving. File to love, nucleo, I guess, for nucleus. Or nuclear? Not nuclear. Certainly not nuclear. Right, so this is a nucleus loving species. And I always just think of it as instead of nucleus, I think of it as just a positive, specifically positive charge loving species. So what loves positive charge? Well, most of all, negative charge, right? So negatively charged species are going to be fantastic nucleophiles. They're going to be like, dude, I have a negative charge. I want positive charge. That's how I work. Negative charge, love that positive charge. Nucleophiles also may not be charged. They may simply be polar molecules. Polar, due to, you guys blame this on induction, correct? Whoa. Oh, that's a really great problem we're going to have to go over. Yeah, so nucleophiles, the book defines them as electron-rich. Yeah, so they can be polar molecules, and my last go-to is anywhere where we have lots of electrons. So our key nucleophiles are going to be atoms who can, nucleophiles are going to be atoms, specifically though, who can donate electrons. So if it's something that's negatively charged and it can't donate its electrons, it's not a nucleophile. It could be really, really polar, but unable to donate electrons for some reason. It's going to make it a bad nucleophile. For something to be a nucleophile, it has to be able to donate electrons. And so the best dudes for this are going to be folks with lone pairs. specifically negatively charged folks with lone pairs. Double bonds. Or atoms that are, what are you guys talking about? Inductive? Or atoms that are electron-rich due to yeah. We're gonna stick with those. Lone pairs and double bonds are going to be our main source of nucleophiles. Yeah. So on the opposite side of the spectrum, for every reaction, pretty much every reaction, we have a nucleophile. We also have an electrophile. Someone who loves electrons. Electron or negative charge loving. So, this is going to be folks who are positively charged. Or folks who are electron E- deficient. And this could be either from an empty p orbital. The chief example of this would be a carbocation. So if we have carbocation, this dude has a vacant p orbital and positive charge like whoa. And so it's like, I need electrons. Please put electrons into my empty p orbital. This should not be. Carbocations are dope electrophiles. They want electrons so bad. So electron deficient could be because of an empty p orbital, or it also could because of polar effects. Another really awesome electrophile are carbonyl carbons. So carbon, who's part of a carbonyl, has this oxygen double bonded to it. This oxygen is very polar. And in being in this double bond, it pulls electrons off of this oxygen like whoa, and gives this oxygen a very strong partial positive charge. Carbonyls are great electrophiles. We can have all sorts of nucleophiles due to low positive charge coming in at this oxygen and being like, I want your positive charge. And the oxygen's like, I want your negative charge. Make it so. So whenever I'm doing mechanisms, or frequently if I'm faced with a reaction that I right off the bat don't understand, I will try and write out a mechanism for it. And the main aspect of my approach to mechanisms is identifying a nucleophile and an electrophile in every step. And I think if you can do that, and we'll definitely go through examples, maybe not tonight a ton, but in the future we definitely will, and we will look at that. And we will see, you will see that identifying nucleophiles and electrophiles is super important. All right, cool. What do we have here? All right, that's pretty much the end of the chapter, actually, and then we can go over some problems. Combining arrow pushing, and what is that? What? All right, so, yeah, at the end of this chapter, the last few sections are all about mechanisms and arrow pushing. We call it arrow pushing because frequently the movement of electrons from one place to another forces other electrons to move, sort of like some musical chairs with folks getting pushed around. So we already briefly talked about the arrows in homolytic versus heterolytic cleavage. We're going to be exclusively talking about, we're going to exclusively talk about heterolytic cleavage. And the book goes through, I guess, a few different types. I kind of like this system of going through general types of arrow pushing we see. Let's really quickly, I'm going to go a little bit out of order, but let's continue to use that reaction that was done in lab as an example. So in lab, we had this alcohol species, and I'm only going to draw the major product. We formed this species. Yeah, all right, yeah, I'm going to hit all these points just a little bit out of order. And we did this in the presence of acid H3PO4. For my purposes, what I like to do when I'm writing out reactions, if we have an acid such as H3PO4, something with a very large counter ion, phosphates and sulfates very rarely themselves participate in the chemistry. They don't do any attacking. If we had something like HCl, it might be a different story, because chlorine can get up in there. It's got a nice concentrate, so it's got a bunch of lone pairs, and it's down to do reacting. But if you see H2SO4 or H3PO4, for most reactions, you can just treat this as being H+. Okay? You know what I forgot to say when we were talking about nucleophiles and electrophiles? Just the important part that nucleophiles, which I'll frequently write as just nuke, are always attacking electrophiles. So our nucleophiles, I write electrophiles as, we might do them as just Ele, or El. We're always going to have our arrows drawn from our nucleophiles to our electrophiles, and these arrows show the flow of electrons. So electrons are always going to be coming from our nucleophiles to our electrophiles. So general types of, let's do this first problem, or let's do this reaction. So our first step, we know that we have this reactant and H3PO4. Those were the only things. And we said that we can treat H3PO4 as H+. So looking at this, does anybody want to guess which of these two species we're going to say is our nucleophile? If we had to assign one, because for every reaction, for every step of a reaction, we're pretty much always going to have a nucleophile and an electrophile. So does anybody want to guess? Our nucleophile, again, is going to have negative charge. It should have lone pairs that it can donate.
Electrophile.
The hydroxyl group, correct. That's going to be our nucleophile. It's the only thing in here, really, that has a lone pair of electrons. And there's no double bond to be our nucleophile either. So we can pretty safely say that this will be our nucleophile, and specifically the hydroxyl group, specifically the oxygen in our hydroxyl group. And since this is our nucleophile, this must be our electrophile. So the first step of this reaction, we're going to draw our nucleophile attacking our electrophile. This is going to happen in every step. Our nucleophile will attack our electrophile. And so like I showed here, we're going to use an arrow to show this. And the arrow is going to be coming from our lone pair of electrons. So I'm going to draw an arrow coming from our lone pair of electrons and have it attacking our electrophile. And this signifies these lone pairs seeing this proton, this H+, and bonding with it. So this is called a proton transfer. And I'm being really lazy here, but what I really should do is show this as PO3 H2. Oh, God, I should just blur. Really, we should show this coming off the phosphate. So I weren't the laziest ever. Proper way to do this would be to show an arrow going to our hydrogen. And this signifies a bond being formed between this oxygen and the hydrogen. Hydrogen can only have one bond. So during any proton transfer step, a lone pair of electrons is going to go to a hydrogen, and that hydrogen, whatever bond it has at that time, will break. This hydrogen will be like, oh, hey, I've got someone new to hang out with. Here, phosphate, you can have these electrons. I got some new ones. They're better. So this is a pretty standard proton transfer step, and a lot of reactions start this way. Lots and lots and lots of reactions start with protonation. Specifically with OH groups getting protonated, like countless reactions begin that way. And so what that does is, let's draw the products of this first step. So we have our protonated alcohol, OH2 plus, our methyl group, and we have H2PO4 minus. So we had a heterolytic cleavage, and as a result, we have two charged species now. And this is, I should show, an equilibrium process. Protonation and deprotonation steps, proton transfer steps, are generally equilibrium processes. They're usually pretty easy to pop back and forth. It's just a little proton. You know, there you have it. Oh, I'll take it back. Cool. So here, actually, I guess this doesn't work super well for my discussion of always a nucleophile and electrophile. This is another type of electron pushing that can happen. So here, this is the only thing we really have to work with. We also have H plus still in solution, but it really can't interact so much. The only thing H plus is pretty much always, it can only be an electrophile, right? It doesn't have a lone pair of electrons to play nucleophile with. We're not going to attack that again and generate a doubly charged oxygen. That's out. That will never happen. So the H plus is not going to get involved in this step. Does anybody know what happens in this step? This step here? I wouldn't expect you to. We haven't gotten to it yet. What happens is we have a leaving group. We lose a leaving group. So what is a leaving group? Well, it's a substituent that is really good at taking its electrons and getting out and leaving. So H2O plus bound in is really good at leaving. Complete molecules are really good at leaving, because if this just takes its electrons and leaves, well, that gives us just a nice water molecule. And that's a nice, happy, stable molecule. So if we have a substituent that can take its electrons with it and then become just a nice, happy, stable molecule, that's a really good leaving group. And the more stable that molecule that it forms is, the better. An example of a really dope leaving group, I can't hold things. An example of a really dope leaving group. Oh, I'm blanking on your name right now, buddy. You're not an EZO, but this guy is real happy to leave. But when it does, we have this lone pair of this bond breaks, and we make nitrogen gas. It was a really stable, happy molecule. So this is an example of a very, very good leaving group here. Something that's very happy to take its electrons and leave. Our halogens are frequently good leaving groups. The larger ones are better. You can usually find tables of leaving groups, but we won't get into that right now. But yes, so here, this process is loss of a leaving group. And I really recommend reading through chapter 6, obviously, because my review is totally not comprehensive. But this is the loss of a leaving group. And frequently this step will not happen all by its lonesome. Frequently we will have a nucleophile that comes in and performs an attack on an electrophile that they're pushing that causes this leaving group to leave. But that's not the case here. The this leaving group just leaves on its own. This is also an equilibrium process. So what's next in this reaction? Well, we know that we have to generate a double bond. So to generate a double bond, we usually do, this is an elimination reaction. We're going to have to, we have a hydrogen here, we're also going to have to remove this hydrogen. And this is going to be done through a nucleophilic attack. Actually, I guess this is technically still a proton transfer. Yeah, this is actually just still technically a proton transfer. Take that back. So we have our hydrogen dangling out here. And we'll have just, another proton transfer that takes us home to our product. So normally hydrogens were attached to sp3 hybridized carbons are not very polar. There's nothing here for normally, if we just looked at this hydrogen in this molecule, that hydrogen is not very acidic. It doesn't want to be pulled off by a base. But since we have this positive charge here, that's going to have an inductive effect on this carbon. It's going to pull electrons away from that carbon because of all this positive charge here. A lot of positive charge pulls electrons from neighbors. And so as a result, this hydrogen is going to have some electrons pulled off of it. It's going to become more positive. As the electrons are pulled in, this bond is going to be weakened. And that makes it feasible for this hydrogen to be removed. So we can either show H2PO4 minus coming in, or that water molecule that we made. In either case, we will show it using its electrons to take this proton. And just like before, when we had a proton transfer, when we made a new bond to that hydrogen, we had to break the bond it was currently participating in. Instead, in this case, we showed this negative charge moving directly onto that oxygen. We're not going to do that in this case. We're not going to move this directly onto the carbon. Instead, it will form a double bond. If we were to draw it going right onto the carbon, we would get a product that looks like this, which is very silly to have a negatively charged carbon directly next to a positively charged carbon. If you ever come up with that while you're doing a mechanism, that should be a double bond. Just so you guys know, if you ever see that, it should be a double bond. So it does not go directly onto the carbon, it goes into the middle, and this leads us to our product. Yay! So I didn't get to show a leaving group attacking. Let's show an example of that. Or a nucleophile attacking. Yeah, let's show that, and then let's do some other pressure. There's a really good problem I really want to do. And then probably wrap up so I can go find some rocks. Right, so yes.
How do you know which one to choose?
Which hydrogen?
No.
Oh, which one of these?
Yeah.
That's a great question. Since these are both sort of solvents, that is a great question. I would be inclined to use water in this case because I believe that is a better base. So in this case, we need to know a little bit about these two different species. I'm not sure if water would be a better base. Which one to use?
Does it not really matter?
It doesn't matter terribly for this problem, I would say. And frequently we'll have situations like that where it doesn't matter. In general, I would say use, frequently we'll have solvents that are able to do this, and the H3PO4 is sort of our solvent here. So I would say it's probably better. Probably is better. That's a great question. Thank you. It would be better to use this H2PO4 minus, sorry. Yeah, frequently in these types of reactions where we have multiple proton transfers, whatever species initially donated the proton will take it back after in a later part of the reaction. And I think in the example that I want to show, we'll see some of that. It's a really long, amazing problem. So this would be really, and we should show our lone pair of electrons. This would really be the optimal way to demonstrate that.
Even though it's like a lot bigger than H2O, it'd still be better.
I would just say for writing out problems,
Okay.
for writing out mechanisms, that would be a better way to do it. You mean just like because of steric bulk?
Yeah, it seems like really big. I don't know. The professor said something about this size.
Yes, so big things do have a harder time getting in. Water would also be good, but there's likely more H3, more of the phosphate species in there since we were using a relatively high concentration of this. There's also a ton of water though because it's an aqueous acid. That's why it's sketchy on this one. But usually I would just use solvents. So for a lot of reactions, we'll have just an acid such as, you can usually use the acid counter ion to do your deprotonations. The conjugate base of the acid we use. That frequently works. Or water or a solvent. Solvents would be better, but we didn't have a solvent here. What am I erasing this for? Right, I wanted to show a nucleophilic attack. So nucleophilic attacks are actually the first type of arrow pushing convention the book talks about, at least in their initial section on arrow pushing. Let's get this chalk nub out of here. It sucks to use. Nucleophilic attack, which I sort of think of proton transfers as nucleophilic attacks. We have a nucleophile that attacks our proton, who's an electrophile. But a nucleophilic attack, this usually refers to a carbon being attacked by a nucleophile. So an electrophilic carbon being attacked. They use, I think, an SN2 example. No, they don't. That's funny. So they show the attack of nucleophile on a carbocation as one example of a nucleophilic attack. So let's say we had this species. A nucleophilic attack would actually be if this water, instead of performing a deprotonation, since we said that this is a reversible process, well, the reverse here is this water using its lone pair of electrons to attack this electrophilic carbocation. This is an example of a nucleophilic attack. Our nucleophile, with its lone pair of electrons, attacks our electrophile's empty p orbital. Another example of a nucleophile and attacking the electrophile, one I particularly love. Let's use a carbanion. Let's say we just have a CH3 minus. This guy, if we introduce this to a carbonyl, C double bond O, let's just say we threw that into some acetone. Well, this negative charge is going to attack our partially positively charged carbon. Remember I said that carbonyls are wonderful electrophiles. Just box off electrophile. So our carbon has a quite strong partial positive charge. Our carbanion has a very strong negative charge, and it attacks the electrophile with its lone pair of electrons. In this case, we're not done with the arrow pushing, because if we left it at this point, every arrow represents a bond that's being formed, right? That's what we've seen thus far. And so if we just made a bond off of this carbon, it would be violating the octet rule. It would have 1, 2, 3, 4, and now a fifth bond. So we have to break one of the bonds on this carbon. Frequently with nucleophilic attacks, a new bond is formed and an old bond is broken. And we see that here, and this is something that happens all the time with, said in an annoying accent, all the time with carbonyl double bonds. We attack the carbonyl carbon. This double bond breaks, and the electrons are pushed up onto this oxygen. So let me erase this guy and show the product of these two reactions. This one up here, you're an equilibrium process. I'm going to put my arrows on the right side. This would give us OH2 plus in our methyl group. So we've added the water onto our molecule through a nucleophilic attack. This other reaction, which is a wonderful way to make carbon-carbon bonds, would give us this deprotonated alcohol now. We've attacked our carbonyl and generated a deprotonated alcohol. Very frequent, very common process with carbonyls. These are both examples of nucleophilic attacks. So we have a species that has a lone pair of electrons attacking a positively charged or partially positively charged element. And very frequently, at least one bond is always formed, and very frequently another bond is going to be broken. And those are kind of the backbones. These processes are the backbones of our using words of our mechanisms. I do want to show one last thing that we'll probably see more of, or in more complicated detail. But let's look at rearrangements really quickly. These will happen frequently with carbocations. And actually, let's use, I erased it. I'm going to use this actually, though, to help me out with that explanation. I'll take this out of here. All right, anyone who's watching this online who paused it and recorded stuff. You guys got that, right? You guys got that? Great. So we said, all right, in this step we have a loss of a leaving group to generate our carbocation. This is actually a fun moment to talk about carbocations. Does anybody know anything about the stability of carbocations? Anybody read about that yet?
They're more stable, more substituents.
Right, more stable with more substituents. So just real quickly, we'll write that over here. Carbocations are more stable with more substituents, particularly electron-rich substituents. Bonus if they're electron-rich. So what does this mean? Well, a primary carbocation, can I make a primary carbocation? I can. Is less stable than a secondary carbocation, which is less stable than a tertiary carbocation. I'm going to pop some hydrogens on this mother sucker. So, with this in mind, does anybody know, what kind of carbocation do we have here? Let's start with that.
Secondary?
Correct. This is a secondary carbocation. And in this process, or in this example, what we have here that's very interesting is we have a tertiary carbon that is next to a secondary carbocation. So tertiary carbons always have one hydrogen on them. And it is a sp3 tertiary carbon specifically. That's an important thing. Actually, just the fact that it's... Nope, that's important. That's sp3. So what can happen here is our molecules thinking, hey, tertiary carbocations are more stable than secondary carbocations. And we can have a really rad thing happen here. We can have a rearrangement. Our molecule can rearrange its bonds to produce a lower energy molecule, a more stable molecule. So this hydrogen can travel with its electrons to this carbocation. It takes its electrons from this carbon out of this bond, and it brings them over to this carbocation. So that basically is like an H-, pops off, and then runs over here. And the result of this. Also, you're probably not an equilibrium process. I don't think that would reverse. There's no reason why that would reverse. The result of this is we move our carbocation to this tertiary position. I don't know why I drew in these other hydrogens, but I will again. So we call this a hydride transfer. Our hydrogen leaves as a hydride, essentially. H minus is a hydride. And it jumps over to where the carbocation is, effectively moving the carbocation to a more stable position. So these are sneaky things that are lovely to put on tests. We can also have, instead of a hydride shift, we can have a methyl shift. But let's not get into that because I want to do this problem. It's long and really badass. Any questions on this guy? So we're only ever going to get a methyl shift or a hydride shift when we can move to a more stable carbocation. We're never going to have, I definitely tried to do this on some mechanism at some point in my undergrad history, and it was just like wrong all over. But if we had, for example, this species, and let's say there's like something cool over here that we're interested in playing with, let's say there's like a PR over there, I don't know. And for some reason we're thinking, we need, for this mechanism, we need to get our hydride here, or carbocation, we're totally clueless, and we're like, well this will just jump there to give us the same thing with our carbocation in a different place, right? That's not going to happen. We're never going to move from a secondary carbocation to another secondary carbocation, unless there's some big deal to stabilize it there. A carbocation, for example, could be stabilized by, if this were an OH bond, then this might happen, because this guy, I still don't think this would happen. No, they're pretty rare. This might happen, because an oxygen can stabilize a carbocation through resonance. So we possibly could have that happening, but I don't think so. All right, let's try and apply all this to this really badass problem in the text. Oh, there's a few of these really badass problems. Uroprotonations and deprotonations. Do we have? All right, that one looks. Oh yeah, that one looks intense. Like camping. Yeah, good one, right?
My lab TA made that joke this morning.
Really?
Yeah.
Oh man, TAs, we're the worst, right? Hey, we all make the worst jokes, because teaching, you gotta fill it with bad jokes. Real bad ones that you laugh at and laugh at yourself.
What number is it?
Let's look at, I'm trying to decide between 644, and 645. They're both pretty sweet, but...
So just for clarification, the carbocation is, the secondary, tertiary, primary doesn't count hydrogens?
No, it is not counting hydrogens when we're talking about a carbocation. Yeah, for carbocations you can kind of just like imagine one hydrogen missing for that. It's a little peculiar. Kind of like in, that's pretty freaking intense actually. We should probably do it. Let's do two. I can't decide, so we'll do two different ones. Let's start with 45. I like 45 because it's a fun intramolecular reaction. What does intramolecular mean? It means a molecule is reacting with itself. They're really sneaky instructors, in my experience, love to put them on exams because they make you think pretty hard in general. Maybe more coffee. I don't have any more coffee. So this reaction is a real fun reaction of this aldehyde species reacting with itself in the presence of aqueous acid. You know what? Let's. The text gives you some steps, but let's try and fumble our way through this a little bit. So we know that in this reaction we have water. It's an aqueous acid. Water is in the mix, and also H+. So, with this knowledge in mind, what I like to do at this point is I like to look at things and say, okay, who here is a good nucleophile? Who here is a good electrophile? And who's maybe a little bit iffy? So water, sorry, not water, I wanted to point to the hydrogen. Our proton, our H+, is always going to be our electrophile. They don't have electrons to give away. It has 0 electrons, so we'll call you L. Our water is essentially both. Water could go either way. It's really good at giving away its protons. It's also pretty decent at attacking. But you know what? I kind of want to skip through this because, well, does anybody have a guess what our first step would be? Just off the top of the bat? Maybe we should go through this the way the text says. I don't really want to because I want to drive this point home. Whenever we have a reaction that's like, hey, it's just in like water and acid, pretty much your first step should always be a protonation. You should always protonate. Somebody's going to get protonated. Yes?
So H3O?
Yeah, we could just be writing it as H3O. That, if we protonate that though, that's really not that interesting at that point. So we could protonate that, and so now we've got H3O and this guy, but H3O doesn't really do any attacking. So that's really just that's not going to help us out too much. The H+ is kind of the same thing as H3O. In fact, let me stop being lazy and say that we have H2O and H3O+, because that's really what's going on. And H3O+ is really just our form that can give away a proton. So this guy gives away protons, this guy can take away protons, or maybe attack as a nucleophile.
So if like we were like on a test, if they said this is like an HCl, it would be okay to just put H+, like in terms of the reaction?
I would do that, yes. That is fine in my book. You might want to check. We should see how Dr. Hill actually goes over, Dr. Instructor goes over mechanisms, but I think that's perfectly acceptable. Some instructors do want you to show where the proton comes from. But for something obvious like HCl, like, come on, dude, it's coming from the HCl. Like, it's a strong acid. Don't break my balls. Vaguely sexist comment. I guess chauvinistic. Patriarchy. Sorry about wasn't the patriarchy there. Get out of there, chalk nub. So our first step, I want to read it, just go over this. With an acid, with an acid, particularly aqueous acids, usually our first step is going to be protonation of our substrate. You guys don't know this yet because you haven't seen a ton of these. But in a reaction like this, we can protonate our water, but we've already got protonated water swimming around. There's really two things that I can think of that could happen. We can have our water behave as a nucleophile and attack our carbonyl, which would behave as an electrophile. That's possibility one. Possibility two is that our carbonyl behaves as the nucleophile, and its lone pair of electrons attacks our protonated water. And we have a proton transfer. And this is like always going to be your first step in acid. Not always, but I'd say 90% of the time, if you have something and you're mixing it up with acid, your first step is going to be a proton transfer. So in this case, yes, our first step will be a proton transfer. And so to be diligent, we should show this bond breaking and moving on to the oxygen. And this will be an equilibrium process, because proton transfers are pretty much always equilibrium processes. I'm going to draw you a little bit smaller this time. But this is also a very important step, particularly because of this carbonyl. When we protonate carbonyl oxygens, what that does is it puts positive charge on this system. It makes our positively charged, not positive, but partially positively charged carbon even more positive. We already said that these carbons are positively charged, or have a partial positive. When we protonate that oxygen, there's even more positive charge surrounding them. There's more positive charge in the system, and they become better electrophiles. They want electrons even more now because of all of this positive charge going on. The oxygen's like, oh, I'm positively, give me more electrons to help me quench this. Right, so this is a very common first step. It really preps this for reaction. Yeah, the book gives us what we're supposed to be working with. Maybe we should just do that. So our second step, we're going to now that we've protonated, now we can attack this. Now this is ready to be attacked. So very frequently we'll protonate a carbonyl and then we'll attack it. So if we have water in the mix, now it's also pretty rare that we'll doubly protonate a species. So you might say, oh, well, and now this guy also will grab a proton, but that's going to put two positive charges on the same molecule, and that's pretty unfavorable. That's going to cause electrostatic interactions that are not so happy. Gesundheit. So a second protonation is unlikely. Again, because we don't want to have multiple charges. We don't want to have like a -2 or a +2 on the same organic species. That's not very happy. It's the simple one. So it's more likely now that we can turn to our water and have this behave as our nucleophile. It sees this carbonyl center, and it's going to attack with its lone pair of electrons, behaving as our nucleophile. I guess actually, before I even say that, just looking at this compound, we should say to ourselves, oh, hey, this is a pretty good electrophile right now, because it has positive charge on it. That's one of our things, one of our checklists, check boxes for looking for electrophiles. And that should help guide us to this decision that it's time to attack it. Right? Let me just put that back. The fact that it has positive charge, the fact that the only other thing we have to interact with really is protons, and we don't want to get a double charge on this, yeah, should tell us that it's an electrophile, and that our next step will be a nucleophilic attack. So we attack this positively charged carbon. Do I have to draw any other arrows in this step? Pi bond, right. I heard break the pi bond. That's correct. Because if we don't break a bond on this carbon, it will have 5 bonds on it. And that's no bueno. That doesn't happen. So we'll break our pi bond. And those electrons will move on to our carbonyl oxygen. Oh, stop squeaking. Ah, I just asked you not to. It's very rude. OH2+. Okay, cool. Step are we going to show first? I suppose since we're in an acidic medium, we'll probably show our protonation first. Yeah. No? What? What? Oh, right. It's not an OH-, it's derp. I totally did that wrong. We already put a hydrogen on it. It was positively charged. So there's a hydrogen there, and now this is nice and happy. Right. So that's part of the driving force for this nucleophilic attack. When this carbonyl carbon is attacked, it pushes the electrons up onto that positively charged oxygen to make it a nice, neutral, happy hydroxyl group. So continuing forward, we have a whole bunch of protonation and deprotonation steps. So this dude with positive charge, very frequently these reactions, once we apply positive charge, we're going to remove it. And we see another water. It's going to come in. And does anybody want to come up and help me with this actually? Does anybody want to come in and draw the arrows for this step? Huh?
First one,
First one?
the carbon,
Come help.
oh, that's right now.
Huh?
I don't know if it's right.
All right, well, where do you think our electrons are going to be coming from? Our crazy guy up here, substrate, or the water?
The water.
Water.
The water, correct. Our water, this is positively charged, as we said, so it's really not in a good state to behave as a nucleophile. So our water is our best candidate for nucleophile. So we'll start with its electrons. And where do we think these electrons are going to go?
Probably to the H.
To the H, correct. We have a positively charged water species here, positively charged species here that we just put on. We don't want to get rid of that. We want to make it more accustomed, more happy in its new home. So we're going to do a deprotonation step. So we'll draw our electrons going to this hydrogen, this proton, and as a result we have to break the bond the proton is part of. Those electrons will go back onto this oxygen. We are running out of space. Let's flip back to the beginning. Get out of here, starting material. So this is going to.
I have a question.
Yes.
So like I'm looking at this molecule and like both of those, so both the oxygens have like, I mean there's definitely like a sort of, oh it's positive. Okay, never mind.
Why the lower one was attacked?
Because I was assuming that the hydrogen attached to the carbon that like.
This hydrogen would be removed?
Yeah.
Okay, yeah. So, that is, why we would go
those
after that.
oxygens are like taking electrons from that bond. I feel like the oxygens would be a little bit more negative.
A little bit more, yes, a little bit more destabilized. That does make sense. We don't very frequently deprotonate carbonyl. We don't frequently deprotonate at that position. Rarely do we deprotonate aldehydes. I can't think of many mechanisms that involve a deprotonation.
So you always attack the positive, that's why you didn't attack the other carbonyl.
That's correct. Also, this is a more positive location to be attacked. It's easier to pick this off for a variety of reasons. It's kind of hard to attack that carbonyl carbon because you have to navigate in there. While this hydrogen is kind of just dangling out away from the molecule. There's less steric interactions on the attack on this hydrogen. And also, there is more positive charge here. This is a full-blown positive charge that's extended out to this hydrogen. Or not extended out, but influencing this hydrogen, while the carbonyl is only a partial positive
That's
charge.
the electrophile, right?
Yes, this is our electrophile.
And the other one's a nucleophile.
Correct, because
it
our
wants-
nucleophile attacks.
It wants to attack the positive because it's positive nothing.
Yes, precisely. So after that step, please don't squeak. We have our two OHs. Am I drawing that right? I feel like I left something out. Yeah, I did. Didn't make it big enough. Didn't make it big enough. So we're back to here. And the book tells us that our next reagent that's going to come into play is some H3O plus. Some H3O plus. So, does anybody, we can say since we have H3O plus, this is definitely going to behave as an electrophile, which means that this substrate will be our nucleophile. Where do you guys think, does anybody want to venture a guess, which lone pair of electrons we'll be using? Do you guys think we'll be using this carbonyl carbons, carbonyl oxygens lone pairs, or the lone pairs from one of these hydroxyl groups?
Hydroxyl?
The hydroxyl groups sounds like a good idea, and actually that step will be very easy. That will happen very readily. But if we look at our reaction, that's just where we came from. We had a protonated hydroxyl group. So reprotonating that, that's just kind of going back to here, back through that equilibrium. So we can rule out using the hydroxyl groups, right? Because we just had that. That was just the structure we were looking at. And we plucked it off. So it makes sense now that we'll put our proton in a different place, right? Makes sense that this lone pair of electrons now will do the attacking. And that should be exciting. I hope you guys are excited now, because like we saw before, when we protonate a carbonyl oxygen, that gets the carbonyl carbon ready to do some chemistry. Okay? Like we saw before, once this guy is protonated, this carbon is ready to do some other frigid science. So let's draw what that gives us down here. So we've got our blam. Okay, cool. Let's okay, so we've done another protonation step in proton transfer. And like I said, this makes our carbonyl carbon really good, real juicy, real electrophilic. Super electrophilic. So we could potentially attack this with more water. But this is where this problem gets really fun. And for this problem, the text indicates that no other reagents are involved in this next step. That means something happens just with this molecule. Can anybody want to venture a guess as to what happens?
Is it the pi bond breaks?
It does involve the pi bond breaking, but that's not going to happen on its own. It's not going to be spontaneous.
Is it hydrogen? You just guess.
Is it gonna like go to a more stable state?
It will work towards that. It's pretty tricky. It's pretty sneaky. So what happens here is we have our intramolecular reaction. And this is pretty cool. When you see a molecule that has that's just a single chain and has funky functional groups on either sides, it's very possible you might be looking at an intramolecular reaction. Because what happens is one side of this chain, the chain folds over, and this guy is going to come around and attack our carbonyl. And that will, like you said, lead to our pi bond breaking. Because like in the other steps, we cannot have a 5-coordinate, a 5-bonded carbon. So this is our intramolecular nucleophilic attack.
So with the intermolecular things, usually it's going to involve, it's going to be a nucleophilic attack on an electrophilic site?
Pretty much, yeah. If you have a good nucleophilic site and a really good electrophilic site on the same molecule, and there's sufficient distance between them in a carbon chain for it to fold over. So if this is nice, because we end up with a 1, 2, 3, 4, 5, 6, I count from the nucleophile to the electrophile to figure out how big our chain is. This is going to make a six-membered ring. And those are nice and stable. 5- and 6-membered rings, thumbs up. You will pretty much never have an intramolecular reaction, specifically, intramolecular reaction to form a 4-membered ring. That's going to be very difficult because 4-membered rings are very unstable.
So basically, you have like a strong, very strong nucleophile, and it just like they're attracted to each other and they form a ring. Is that how that happens?
Yes, and so this is also a very flexible chain.
Yeah.
So if I were to redraw this a little bit more rad, I would show this like
That makes a little more sense. They're right next to each other on the.
yep, so it bends so that they are right next to each other, and then this just does the attack right there.
No.
So these are the same, these show the same thing. People are standing outside like they want to be in here. Don't, oh shit, I gotta wrap this up. Right, so that is our fun intramolecular reaction. And then our final step is just going to be one more deprotonation. So this gives us our 6-membered ring, an oxygen there. Right now we have an OH there. Oh, and you have an H on you. Is that what we got? Yeah, that's what we got for right now. So our last step is going to be just deprotonating this oxygen. And that will give us a nice stable molecule. A nice stable hemiacetal. Oh, fun. This is called a hemiacetal because we have an oxygen or a carbon who's bound to an OH and also an ether. That's a hemiacetal. Jasmines. Yeah, so this gives us our final product of OH, OH, and a cool ether in the middle. Pretty sweet shit, right? Dude, mechanisms are so rad. Yeah, these people are clamoring to come inside, but I'm like keen on doing just one more real quick problem before we wrap this up. It is a super, much more complicated one from the looks of it, but it also has more variety in it, and variety is the spice of life. So we gotta get it. We gotta get that. So this one is problem 654. 654, and it shows, it's so complicated. This lovely, we've got an epoxide in here. This is an epoxide. And we also have, what are you? You're an imid? Imid? I'm not sure exactly what your name is. We have an ME, cool, and the book does that too. You guys are all familiar that, hopefully that ME is the same thing as writing a CH3. Just takes a little bit less time for us lazy-ass chemists. We have this fun species up here. And we're asked to draw in and do some arrow pushing. So our first step, all we're told is we're treating this with OH minus. So, what do you guys think? Which one of these is going to be our nucleophile? Which one's going to be our electrophile?
So the COs are,
Is there a dot on that?
oh, never mind.
That was confusing,
okay,
sorry.
okay.
Let me get it to 654. Consolidate, you know. Does anybody want to take a guess?
CO has a ton of
The electrons.
electrons, so I'm assuming it's going to be
Our nucleophile? That's some fairly good reasoning. But if we said this is going to be our nucleophile, that would mean this is going to be our electrophile.
Isn't it the other way around?
Yeah, this doesn't make any sense as an electrophile. Makes no sense as an electrophile. Negatively charged electrophile? What? Negatively charged folks don't want negative
That's
charge.
a nucleophile.
Right, so this would be our nucleophile by default, and this would be our electrophile. And actually, this problem shows us what the next material is. So let's not make this super big ruling, because you guys obviously have no idea where this would come into attack. Let's just get our next structure in and see if we can figure out what arrow pushing we need to do, because this is fairly complicated. Oh, it's so good. It's so good. Check that out. So, looking at this now, does anybody have any idea where our nucleophile attacked? The H, correct.
Yeah.
We have this hydrogen in our starting material, and we don't have it in our product. Also, this is a hydrogen that's sitting on a nitrogen. Hydrogens on heteroatoms are usually very easy to yank off through proton transfers. But clearly a whole bunch of crap happened because of that. So we're going to have to explore why all that happened. But for starters, to begin our mechanism drawing, we can say, all right, our OH minus grabbed this hydrogen. And so we might be tempted to say, and the electrons went directly onto the nitrogen. But that's not going to account for all the crazy sniz that happened over here. And we also can see that there is a double bond on this nitrogen that lost the hydrogen. That's a pretty good indication that instead of depositing its electrons directly onto this nitrogen, that these electrons form a double bond. And that's very similar to what we saw in that elimination reaction we talked about earlier, where we had a carbocation and we had our H2PO4 minus do proton transfer to remove this proton and form a double bond. Similar stuff, right?
Well, technically, doesn't nitrogen trivalent, so doesn't have a lone pair already? So why would it make sense to put another lone pair?
Another lone pair on it?
Yeah, so why would you put two lone pairs on it? Can't you just? Is that why the double bond is formed?
That's part of why the double bond is formed. You can have two lone pairs on nitrogen, but
Yes.
they don't really like to be negatively charged. They're not super stoked on that. So this is going to form a double bond, which in turn means we have to break this double bond or do something else here, and that's our only option, because otherwise this nitrogen will have too many electrons. It'll violate the octet. We would have 1, 2, 3, 4 bonds and a lone pair. No good. So we have to break this double bond. Oh my gosh, so where is this double bond going to go? Over here? Well, it can't really go over there because that would make a hydrogen or a carbon that's got too many bonds to it. So it has to move to this side because its ethers or epoxides, which we have here, are fairly easy to break. And we know we can break carbon-oxygen bonds pretty easily. It's pretty freaking hard to break carbon-hydrogen bonds. So if we push it over to this side, now we have this epoxide. Oh my gosh. So we have to break one of these bonds now, since we're putting in a new bond. It's also true for hydrogen. Carbon-carbon bonds are hard to break, and as I said, carbon-hydrogens are hard to break. So it's easiest to break our carbon-oxygen bond. This is also a fairly strained molecule, or the bond angles here are fairly strained. Epoxides are pretty easy to break up. And that should account for everything that we see over there. So this hydrogen was removed. We have our double bond that we formed there. We broke this double bond and formed one here, which we see, and we put a negative charge on our oxygen. Freaking sweet. And, oh my god, really? All right, so then in our next step, this just totally dissociates. This is so freaking rad. Yeah, let's just wrap up with this. This guy dissociates into, can I draw that? Triple bond. Me plus nitrogen plus Cl minus. Holy frick. How did that happen? Holy frick. Well, let's break it down. All right. We know that our only oxygen is going to become a carbonyl. We also know that this ring is going to break open. And we know that we need a triple bond in the ring as well. So it seems very likely that this bond will break. Right? If we were to break this bond, we could move the electrons up into there. The other thing that would actually be really helpful for doing this, that I'm going to say now, is if we just number stuff, it'll make life really easy. So if we number 1, 2, 3, 4, 5, 6, 7. Can we apply this numbering over here? 1, 2, 3, 4, 5, 6, 7. Beautiful. We know that our double bond is going to get bumped up to a triple bond. And we know that this guy is going to break off into its own thing. We really got to get out of here. Where do you guys think our arrow pushing is going to start from? I think guesses
Start from double bond.
Double bond, that's one guess. I heard oxygen. The oxygen is definitely going to be our starting place. There's more negative charge here. We have a full-blown negative charge there. So that's where we've got the most electrons popping. So, and that's cool. That'll make it really easy. We push these electrons down, and we can reform our carbonyl, which we're supposed to have. We know we have to break this bond from our diagram, right? We have a bond between 2 and 7. We no longer have that here. So we can break this bond and push it up there, and that gives us our triple bond. Cool, right? Push another bond into our double bond, gives us a triple bond. We have to get our nitrogens, the F out of there, right? So the nitrogens, we now need to break one of these bonds, and based on our numbering system, we know 5 and 6 are still connected, but 6 is not connected to the nitrogen. So we can break our nitrogen bond, and we can continue to push these electrons around. So these ones are going to get pushed up, and that accounts for our nitrogen-nitrogen triple bond.
No.
And lastly, the chlorine is a leaving group who we kick out. So this is a really cool, this is a, I guess not a rearrangement. We could call it rearrangement, but it's a rearrangement that involves the loss of a leaving group. Very cool problem that I like a lot. And let's get out of here so this other class can come in and do some really great learning. And bye, people in computer land. Let's turn off the
You do this
recording.
every week?
Yeah, doing this every week.